Okay, good day. This is dual enrollment pre-calculus. I am Mr. McCulley, and this is lesson number 12, definition of logarithm. Let's get right to it. So the learning goals for today comes from section 3.2 in the text. We're going to recognize and evaluate logarithmic functions with base A. We're going to graph a few logarithmic functions. We're going to recognize and evaluate, and graph, there should be a comma there, sorry, natural logarithmic functions, and then use logarithmic functions to model data and solve problems. So let's get right to the definition there. Definition of logarithm is this. If log base a of x equals y, or log base a of x equal to y, and again, that's how we read this, log base a of x equal to y, if and only if a to the y equals x. So basically, it's taking an exponential that we had in the last section and changing it into a different form. And this form is going to end up being an inverse. It's going to help us find inverses of exponentials and do some other fun things with it. So real quick, some sample properties. These sample properties all derive from the definition of logarithm. So if I say log base a of 1 is equal to 0, because if I transform this, or if I use the definition to transform from logarithm to exponential, a to the 0 equals 1, which is what we have as long as a is not equal to 1. Log base a of a is always equal to 1 because if I take a to the first power, that'll be equal to just a. Log base a of x is equal to x, and also a to log base a of x is equal to x, and again that goes back up to the definition of logarithm. And then finally, and this one is the only non-definition one, if you have log base a of x equal to log base a of y, the only way that that can be true, since I have two logarithms with the same base, is if whatever that expression is, whatever x and y both represent, those two things have to be equal. Let's move on to the next slide, maybe. Hello? Come on, move on. Not responding. I hope it's still recording. There we go. Okay, so the generalized logarithmic function is an inverse of an exponential function. The domain of the generalized logarithmic function is all reals greater than 0, which we already, well, I guess would make sense since I said it's an inverse. And therefore, since the range of the exponential is all real numbers greater than 0, when you flip your x and y to get the inverse, the domain of the logarithm would be all real numbers greater than 0. All right, so we get our graph, and again, we see that anytime that you do an inverse, it's a reflection about the line y equals x. So y equals a to the x becomes the logarithm function log base a of x. And so we get that. Now, there are two consequences of this thing. And so if I talk about the domain and range of just our generalized logarithmic function, so if I say y equals log base a of x, its domain will be all reals where x is greater than 0, and the range will be all real numbers. All right, so that's our generalized logarithmic function. Some known logarithms, and when I say known, I put it in parentheses because we really can know any logarithm, but the graphing calculator has two logarithms built in, and you can do other bases, but we have ln and log on the graphing calculator. And so ln is just log base e, and when you see a logarithm with no value here, we're going to consider it to be log base 10. And so you can kind of think of that log of x is always base 10, the same way that you say that x is always equal to x to the first, or x over 1 is always equal to x, or the square root of x is equal to the second root of x. Okay, so just as a generalization in a form, if you see no value there, you assume it's 10. And that makes sense. Log base 10 because our number system is on base 10, and ln is used quite a bit because exponential growth, continuous growth is also used quite a bit. All right, so that's really all the new stuff, I think. So let's get into some discussion here. We really have the big use of logarithms in the real world is this, and we're not going to get to it a whole lot today, but as we move through the rest of the chapter, this is going to be the main use of learning logarithms. So I look at this as an example, and I can say this is easy to solve. All right, it's easy to solve. 3 to what power is 9? Well, obviously x has to equal 2. And as long as this value here is a perfect power of the base, and we're just using counting numbers for the variable, those are real easy to solve. The problem arises is when I go, what is if 10 equals 3 to the x? Now, I know that this x has to be greater than 2, and x has to be less than 3, because I know that 3 to the third is 27. I also know that it's probably closer to 2 than it is to 3, but other than that, I don't have a really good method of solving for x and being anywhere accurate. So logarithms are going to help us solve this. All right, so we're going to get to how to do that. But first, let's talk about manipulating logarithms. So first thing, a couple of elementary examples that you'll see probably on the first quiz. Convert log base 2 of 32 equal to fifth to exponential form. Well, again, that's just using the definition of logarithm. So we could say that 2 to the 5 is equal to 32, and clearly 2 to the 5 is equal to 32. And for these in the book, and on my test, if this thing isn't true, then you probably made a mistake there. And so doing the reverse, we're giving an exponential. They want us to change it to a logarithm. Sorry. This will be log base 6 of 216 is equal to 3. And so those are two real simple examples. Next example. Come on, go. There we go. Use the definition and properties of logarithms to solve. So we want to solve this thing. So I come down here, I say log base 3 of 3. Well, let's see, do I have one like that? Well, number 3 here, log base a of a to the x is equal to x. Okay, so if I have the same base and the same value, then this number is the same as that number. Okay, well, we can do that. So using that property, we can conclude that our x here has to be equal to that value there, -5. And we're done with that one as well. All right, next. It says, describe the transformation from f to g. And so I look at this as my general logarithm. And so when I look at this thing, I see two transformations. And even though it's a new function, logarithmic function, the rules that we talked about for transformations from the first lesson, I've got this x minus 1 and I've got this plus 4 here. So I see two transformations, 1, 2. And again, we're just going to say let x equal to 10 That works because 10 is in the domain. And see what happens. When I plug in 10, what's the first thing that happens? Well, I subtract 1. So, since I'm subtracting 1 from that value, that means I'm subtracting from the variable. So that's going to mean translate 1 unit right. Okay. So after I've subtracted 1, then I'm going to take the logarithm, base 8 of that thing. All right, so that's now the function, and now I'm adding 4 to the function value. Well, when you add to the function, you translate up. And so those are our transformations, and again, we are finished. All right, use property of logarithms to simplify the following. Okay, well, let's talk about this. ln e is the same as log base e, so I have a negative out front, and so I'm changing this to log base e of e. And we already know from our properties here that log base a of a is going to equal to 1, and I picked this one especially because ln of e equaling to 1 is going to save us a lot of work as we move forward. So this thing, and again, you don't have to necessarily do all of the steps, but just to be clear, I have the negative out front that was still there. Log base e of e we know to be 1, and so this thing ends up just being negative 1. So we're done there. All right, so e to the ln of 22. Okay, well, we have, again, we go back to our properties list, and I see that if I have a raised to the log base a of x, it's just x again. All right, so in this particular instance, since we have an ln, it's e and log base e. So let's write that all out here. So this oh yeah, let's do that. E log base e of 22. And when you have a to the log base a of some value, it's just that value. So this thing equals 22, and we'll close that off. And then here again on the last one, I am going to convert this 1 over 4, and I'm going to use the fact that a to the negative x is equal to 1 over a to the positive x. And I'm going to do it in reverse. Since I have 1 over e to the 4th, I'm going to rewrite this as ln e to the negative 4. And remembering that ln is log base e, I have log base e of e to the negative 4th. And so just like in the, similar to this last one, but using that property, log base a of a to the x is just equal to x. So log base e of e to the negative 4th is just equal to negative 4, and we are finished. No, that one's a short one there, folks, but that's all I got for today. So the Super Fabu fun fact, Star Wars fun fact of the day is if Carrie Fisher, who played Princess Leia and has since left us, she was not going to be available to play Princess Leia. George Lucas's second choice was to be Jodie Foster from Silence of the Lambs fame. And that's all I got for today, folks. So have a good one. Goodbye.